People, here's a typical sort of rotational or rolling object problem. And most of those, the standard ones, I would say, deal with conservation of mechanical energy. All right, so we're going to look at that as it applies to a couple of different objects here. One of them is a basketball, and the other one is a can of frozen orange juice. Sure. Interesting. Anyway, so let's see. Starting from rest of basketball rolls from the top of a hill to the bottom. Okay, so fine. Starting from rest. We go from there to here. Here we're doing this. So what's the height of the hill? We have a speed at the end. Okay, so I'm going to start by using conservation of mechanical energy. All right, and we can write all the terms for each side, which you might not choose to if you choose to eliminate a couple things right off the bat. But if we're looking at all of them, the mechanical energy of one of these objects can be expressed as its GPE plus its translational kinetic energy plus its rotational kinetic energy. So there's a term for each of those initially and finally. GPE final plus KE translational final plus KE rotational final. All right. Now, that basically gets rid of both of those. Center of mass is not moving. It's not rolling. All right. In the end, it gets to where we'll call zero height, but it is moving as a, well, as a whole object. It's moving down the hill and it's rolling. Okay, so this turns into GPE initial, MGH initial equals KE final 1/2 mv squared. It's the translational kinetic energy plus KE rotational 1/2 I omega squared. Now I just had to pause to look up the moment of inertia of a hollow sphere, but hollow sphere 2/3 mr squared. So here's what will happen. We'll keep the MGH. We'll certainly keep this, and we'll say, all right, this is 1/2 I 2/3 mr squared. Omega, this goes back to our look at rolling motion, where we said that an object that's rolling has a center of mass velocity, and it also has, well, if it's rolling this way, it also has these tangential velocities anywhere on the rim there. And what we figured out in our look at rolling motion is that, well, the center of mass velocity and the VT are both equal to R omega, R omega. So that means that the tangential speed that we use in our expression for, or as part of an expression for omega, is the same thing as the center of mass velocity, which we use for our translational kinetic energy. So that means we can write omega, well, check this out. We can write omega as V, well, I really should use this one, as V center of mass over R. So from here, omega is V over R, where, moral of the story, V over R. Now, it's omega squared, so I'm just going to square both of these. And what I'm really trying to make sure we point out is that this V and this V are the same thing. Big deal, same thing. All right. Now this R and this R also same thing. So that means that these can go away. And look what we end up with. MGH initial equals 1/2 MV final squared plus, let's see, 1/2 times 2/3. That's well, that's 1/3 M. Oh, V squared. Look at that. And it is V final. Yeah? Now we can get rid of a factor of M everywhere. Or you can do that in the next step. And we have, let's see, GH initial is, well, we have VF squared over 2 plus VF squared over 3. So this is really like 3/6 VF squared plus 2/6 VF squared. So GH initial is 5 VF squared over 6. That could be looking for. Oh, the height of the hill. Great. So the height of the hill is 5 VF squared over 6G. Or 5 VF squared, 6.6. Don't forget to square over 6G. That's 40, it's 200 divided by 60 is, yeah, sure. 3.7, I buy it. Okay, so big deals. One is we typically, now if you notice, I bet they don't even tell us, yeah, basketball. They don't mention anything about the radius of the basketball, right? Because you don't need it. If you turn your I omega squared term into the expanded form of each one, here's I, here's omega, one has an R squared, one has a divided by R squared, those R squareds divide away. Okay, and what's also nice is we end up with two terms, each with mv squared. And it's a matter of how you add those fractions. Okay, also, let's just point out again, right? The v here that we use in omega is v over r, and the v here that we use for the center of mass velocity are the same velocity. That's why we can combine those VFs. Okay? Now the next part, give me a moment to do some housekeeping here. Yeah, sure. Get rid of this. So we still should have that term here. Oh no, we're fine. So sorry, the next part is about what if we let a can of frozen juice roll to the bottom of the same hill? What's the translational speed the frozen juice can? What is the yeah? All right. So this is now not a sphere, a hollow sphere, but a cylinder. And even though it's a can of frozen juice, I guess I'm going to assume that's a solid cylinder. All right. Now, a solid cylinder's moment of inertia. I'm on the old Wikipedia here. Solid cylinder. Here we are. Right. Okay. Okay. Whoa, I don't like that. Oh yeah, sure I do. Here's solid cylinder. About this z-axis. So if it rolls, the moment of inertia is just 1/2 mr squared. Okay, so go back here. This is now a solid cylinder. And so we start in the same way. Well, with this, well, I'm just going to jump right to here. GPE initial equals, well, you know what? I'm going to skip that step because it's the same thing. Everything's the same up to this point. So we can say that MGH initial equals 1/2 MV final squared plus 1/2 I omega squared. The difference now is that our I turns into 1/2 mr squared. And our omega squared, still that. Our r's still go. We can still take a factor of m out of everything. We end up with G H initial equals 1/2 V final squared plus, well, all we have left is a half times, 1/4 VF squared. GH initial is, well, let's see, a half plus a fourth, that's 3/4, right? 3/4 VF squared. We're looking for the final speed now. So 4/3 GH square root. So let's make sure that they wanted us to assume this really was a solid cylinder can with frozen orange juice. And you know what? Look what doesn't matter. The mass of that orange juice stuff doesn't matter. So 4 divided by 3 times 9.8 times 3.7 equals square root 6.95. Yeah, sure, 7.0. Okay, VF, we'll call it 7.0. Okay, so what to point out here? Well, I mean, the big thing to point out is, if you're taking my course, we don't have to memorize these. You'll be provided with a list of moments of inertia. Just make sure that you're looking for the right one. All right. I think that's the crux of it. Okay. All right, folks. See ya.